Welcome to this custom deep dive. Today we're looking at a really fascinating research paper by N. Majid and team.
Yeah, it's a great one.
It's all about predicting when cast aluminum alloys, specifically A356-T6 and A357-T6, will actually crack under stress.
Right, which is a huge deal for manufacturing. The mission here is to uncover how they use this clever blend of old school physics and, modern machine learning.
So they can design lighter, eco-friendly car parts without spending years just breaking them in a lab.
Exactly. Because physical fatigue testing is just painfully slow and expensive.
Okay, let's unpack this for you. Testing fatigue is, it's basically like bending a paperclip back and forth until it snaps.
Right, but on a massive industrial scale.
Right, and waiting for those industrial paperclips to break is a huge bottleneck for engineers.
He really is.
Yeah.
And to understand why it snaps, you have to look at this microscopic tug-of-war happening inside the metal.
A tug-of-war between what?
Well, two forces mainly. First, you have SDS, which is secondary dendrite arm spacing.
SDAS. Right, that's dictated by cooling rates, right? Like, it gives the metal its inherent strength.
Spot on. But on the other side of the rope, you have microscopic casting defects.
Like, gas pores or shrinkage cavity.
Yeah, exactly.
Yeah.
The researchers looked at the surface area of these microscopic defects because they act as crack initiators. They're where the break actually starts.
Oh, I see. So it's the strength of the SDS battling against the size of those tiny defect areas.
Precisely. But here is where the data scarcity problem comes in. Machine learning could skip the physical testing entirely, but it usually needs massive data sets.
Right, and here's where it gets really interesting to me, because they only had like 16 real-world data points for this A356 alloy.
Just 16.
How do you possibly train a reliable AI on just 16 points? I mean, it would just memorize them and fail on anything new, right?
It absolutely would.
Yeah.
But they found a brilliant workaround. They didn't just rely on the raw data.
Okay, so what did they do instead?
They took an existing, trusted empirical physics equation and used it to generate a massive synthetic data set, like 5,000 points.
Wait, really? They just generated 5,000 artificial test results?
Yeah. By doing that, they forced the AI to learn the fundamental physical rules of the metal.
Oh, wow. So instead of just blindly memorizing 16 numbers, it's learning the actual physics of how the metal breaks. That is a really clever hybrid solution.
It is. And then they had a sort of AI bake-off to see which model handled it best.
Right. They tested 3 models, didn't they? SVR, random forest, and Gaussian process regression.
Yeah, and support vector regression, or SVR, completely won out.
By how much?
It captured the fatigue limits with a stunning 95.7% accuracy.
Wow, an R-squared of 0.957. That's actually crazy.
And less than 2 megapascals of error. But what's really fascinating here is the ultimate flex they did next.
Oh, right. They took the SVR model, which was trained entirely on the A356-T6 alloy, and they tested it on a completely different alloy, the A357-T6.
And it successfully predicted the new alloy's fatigue.
That is the real flex. It proves the AI wasn't just a black box. It had actually learned those universal metallurgical interactions.
Exactly. It learned the rules, not just the raw data.
So what does this all mean for you listening? Basically, it means faster innovation.
Right. This framework lets engineers confidently design safer, lighter vehicles much, much faster.
No more waiting around for months just to see when a piece of metal is going to snap.
But this raises an important question to leave you with. This model assumed the microscopic defects were perfectly spherical.
Which, they almost never are in reality.
Right. So how might this hybrid AI framework need to adapt to predict failures from the chaotic, wildly irregular defect shapes you actually find in real-world manufacturing?